Hello students, my name is Shashank Shekhar and today is the fourth lecture of the chapter Aldehyde Ketone and Carboxylic acid. So today we will be seeing the reactivity of this carbonyl compound, that is aldehyde and ketone. So we have seen all the preparation method that are used for the making of this aldehyde and ketone, all these general reactions as well as some specified reaction. Okay, so where are we? We are here. Also, we will also cover today physical and chemical properties as well. Then we will see how this mechanism goes. Means this chemical properties is basically related to the nucleophilic substitution. So we will see the mechanism of nucleophilic substitution or addition, I would say. Okay. Regarding the reactivity of alpha hydrogen, this is specific to your say aldol and aldol reaction that would be covered tomorrow. Aldol reaction and Cannizzaro reaction. Clear? Basically, today we will be seeing all these reactions that are not that much emphasized, but the reactivity of all the aldehyde and ketone are based on this nucleophilic addition only. The name reactions like our aldol reaction or Cannizzaro reaction, that we will discuss tomorrow. So if you look at today's topic that will be covered, the first we will see the physical state of what is the physical state of aldehyde and ketone based on their length. Then we will see the boiling point. After that, we will be covering solubility. And then we will see an exercise and compare the boiling point of some common functional group which we have studied till date. Clear? Then again we will see the structure of carbonyl group which I have covered in the first class of the aldehyde ketone and carboxylic acid chapter. So we will cover this again because to look at the reactivity, you must be clear about the structure, how the structure looks like. Then as we get the idea of structure, we will move to the mechanistic part of the nucleophilic addition reaction. And as we saw the mechanistic part, then we will be able to predict the reactivity, that what are the factors that are affecting the reactivity once we are get well versed with this mechanism. And at last we will see some examples of nucleophilic addition. Other than this, we will also see oxidation and reduction of aldehyde and ketones. So regarding oxidation, we will see ketone tolerance test and Fehling test and the haloform reaction. And regarding reduction, we will see two types of reduction: Wolff-Kishner reduction and Clemmensen reduction. Okay, so these are the topics for today's class. Now first let us start from the physical state. So if you see at methanol, that is the first group of this aldehyde group, it is gas at room temperature. Okay, so as we increase the size, or you can say the molecular size of the aldehyde, the state changes to liquid. Okay, so you can see that ethanol is volatile liquid and other aldehyde or ketone, they are present at solid at room temperature, liquid or solid at room temperature. So you can see very clearly that only the first member of this group, that is the methanol, is having a gaseous phase or a gaseous state. Other than this, methanol, the ethanol or the other aldehyde and ketone are solid, are in fact liquid also. So liquid are in fact solid also. So why is this happening? The reason is very simple. So as we are increasing the molecular mass, the van der Waals force is increasing between the molecules of the compound, and the interaction, due to the increase in interaction, they are forming a much more stronger bond. I would not say bond, a stronger interaction. Clear? Then due to this reason, they come closer and they form solid. And we know very well that the gaseous molecules are far apart as compared to liquid. Then the solid molecules are very close, very close as compared to liquid. So you can predict, or you can say you can demonstrate the idea of solid, liquid and gas on the basis of the distance between the molecules. So in gases, the distance is the largest, and in the liquid is in the mid-core, and solid has the least distance between its molecules. And the reason is their interaction. Okay, so as we have increased the molecular mass, so we have increased the interaction, and hence on increasing the mass, we are getting the state changing from gas to liquid to solid. Clear? Now let us move to the boiling point. So the boiling point of aldehyde and ketone, so as we have seen always that the functional group has generally higher boiling point as compared to the simple hydrocarbon, because simple hydrocarbon has no such type of interaction like dipole-dipole interaction or hydrogen bonding. There is no such interaction because it is a linear chain and it has only carbon in it, due to which there is no development of polarity in the molecule. But as we compare it to the aldehyde or ketone, as we will see in the next lecture upcoming slides, that there is a polarity in the bond. Due to the polarity in the bond, there is induced a positive and a negative charge. Depending upon the electronegativity, there is a induction of positive and negative charge. So carbon has a positive charge and oxygen has a negative charge. Now the other molecule has also the same type of charge distribution. As we know very well from the electrostatics, you must have studied in physics, that opposite charges attract each other. So the negative part of one molecule attract the positive part of other molecule. Similarly, the positive part of the latter molecule attracts the positive part of the former molecule. Clear? Also, it is higher than ethers. So we will see the demonstration when we will do the exercise. You will see why is this so? Why is the dipole moment less? You must have seen in the alcohol, phenol and ether also, but we will just make a quick review of that also. Clear? Now it is due to the weak molecular association of aldehyde and ketone arising of dipole-dipole interaction. The same thing is written here. As I have told that due to the change in electronegativity or the difference in electronegativity between carbon and oxygen, there is an evolution of positive and negative charge. The negative charge on the oxygen and the positive charge on the carbon. This creates a dipole, and two dipoles interact due to the opposite charges attract each other, and hence a dipole interaction is set up. And due to this reason, the boiling point of the aldehyde and ketone is higher than as compared to your simple hydrocarbons or ethers. Okay. Also, their boiling points are lower than those of alcohol. This should be noted very clearly, that the boiling point of alcohols are greater as compared to aldehyde and ketone, and the reason is very obvious. It is due to the intermolecular hydrogen bonding. Now you can make a point here that okay, some of the points are that your intermolecular hydrogen bonding is stronger than your dipole-dipole interaction, which is in turn stronger than the van der Waals interaction. And due to this reason, we see such a trend that alcohol has the highest boiling point, then comes the aldehyde ketone, then our ether, and at last comes our hydrocarbon, which has just van der Waals interaction. Clear? So it is written that the alcohol has greater boiling point because there is no intermolecular hydrogen bonding in aldehyde or ketone. For intermolecular hydrogen bonding, there should be a hydrogen attached to an electronegative element like oxygen, or say we have nitrogen. Okay, and in that case only it will be attracted to another electronegative element like oxygen and nitrogen. It can be fluorine also. So if hydrogen is attached to fluorine, in that case also we can observe this hydrogen bonding, intermolecular hydrogen bonding. Now let us see a chart here that would demonstrate what is the trend of boiling point in this functional groups. One thing is to be noticed here, that we have tried to keep this molecular mass in between 58 and 60. Why are we doing this? Why are we limiting or putting barriers on this molecular mass? So that other interaction like van der Waals cannot change the perspective of this. Okay, so suppose if we do not keep one of the parameter constant, and we are trying to say compare two things that is based on another parameter, this would create confusion that which parameter is dominating. So what we have done, we have kept one parameter constant. What is that parameter? That is van der Waals interaction constant, because van der Waals interaction is dependent upon molecular mass. So if we control the molecular mass, we will also control the van der Waals interaction. Due to this reason, now we can only focus on the other interaction. Clear? Now let us see the demonstration. So first we have a normal butane whose boiling point is 273 and molecular mass is 58. Okay. Then we have methoxymethane. Now you can see that as we move from this normal alkane to your this is ester. If you don't know, sorry, not ester, it is ether. Okay. It is methoxyethane. Structure looks like this: CH3O C2H5. So this is the structure of methoxymethane. This is a ether. Now it has a higher boiling point as compared to N-butane, and you can see that molecular mass has not varied much. It is 60, and I am telling that the change of molecular mass by such small units like 1 or 2 would not predominantly affect the van der Waals interaction. There should be a large difference in molecular mass, like a difference of 20 or 30, and in that case only we will be able to see this changes in boiling point due to van der Waals interaction. Clear? Then we have moved to propanol, that is aldehyde. You can see that there is a great change. Okay, there's a large difference between its boiling point. You can see that this difference is not that much large. It is 273 to 281. That is approximately of 7 plus 1, 8 unit change, or you can say 8 degrees Celsius, 8 Kelvin, anything, because change in temperature is not dependent upon your this thing, that is your unit. Clear? So, and as we move from this methoxyethane to propanol, we have seen a drastic change of 281 to 322. So that is approximately of 40 unit changes. And why is it so? As I've told you earlier, that it has a greater dipole moment as compared to your ether. And you can see the molecular mass is also comparable. It is 58 and 60. There is no significant change in the molecular mass also. But still, we have seen a significant change in this, our say boiling point. Okay, clear? Next is our acetone. Now acetone has a greater boiling point as compared to your aldehyde. We will see to it why is it so. We will see to it. Okay, we'll see an illustration. How can we compare the molecular mass, boiling point of your aldehyde and ketone, and what is the reason this is high? We will see to that. At last, we have a propanol, which is a alcohol, and alcohol, as you can see, it has a very high boiling point as compared to all of this functional group. And why is it so? It is due to the intermolecular hydrogen bonding. So again, I am repeating it, that intermolecular hydrogen bonding has the highest priority in case of comparison of boiling point, because this interaction is the strongest one. Then comes your then comes your dipole-dipole interaction. At last comes your van der Waals interaction. And here also we have kept this thing almost comparable. So this was about the physical state. So first we have seen that methanol has the gaseous state, and as we increase the molecular mass, the van der Waals interaction increases and the state changes from gas to liquid to solid. Then we have the boiling point. So in boiling point, we have seen that, okay, this is due to the interaction, dipole-dipole interaction, that aldehyde and ketone have a greater interaction and a greater boiling point as compared to ether, and ether has a greater boiling point as compared to your normal propane, butane, or any other alkane. Okay, so this was about the physical state and boiling point. Now next we will move to another physical property, that is solubility. Now solubility, if you remember in the previous classes, that we have seen the solubility and compared the solubility of your alcohol, and the major contributing factor which increases the solubility was hydrogen bonding. So here also we have the same factor. So it is written here that the lower member of the aldehyde and ketone, such as methanol, ethane, and propanol, are miscible with water in all proportion, but they form hydrogen bonding with water. Miscible means soluble in water. What it is? Soluble in water. So the lower groups, that is methanol or ethanol, they are soluble in water. And if we talk about ketone, we have propanol. So they are miscible in water. But as we move to higher functional groups, okay, so higher homologous series, I would say, then you would see that there is a decrease in solubility of your functional group or the compound. So it is written also that the solubility of this aldehyde and ketone decrease rapidly on increasing the length of the alkyl chain. Why is it so? So if you see the dipole moment here, so we can see that we have a delta positive charge on the carbon. Now if in any way this positive charge is being neutralized by any other alkane or alkyl chain, then that would result in decrease of the dipole moment overall. And decrease in dipole moment would result in weaker dipole-dipole interaction between water molecule and your carbonyl. And how this length chain is decreasing? So decreasing the dipole moment or increasing the negative charge on carbon, because as we increase the our length chain, there would be increase in the inductive effect. So more lengthened chain, or you can say longer chain, have a greater inductive effect, and therefore it donates more electron on the carbon that is having a positive charge or the partial positive charge. So all aldehyde and ketone are fairly soluble in organic solvent like benzene, ether, methane, and chloroform. So this statement that has been made here is a direct consequence of the statement that this is a standard statement that like dissolved in like. So if it is a non-polar solvent, then it will dissolve the non-polar solute. So you may argue that why aldehyde and ketone are polar in nature, but see students, one difference is there between this polarity and the polarity of the polar molecules, higher polar molecule like HF. Their difference in electronegativity is very high. So if you compare the difference in electronegativity of carbon and oxygen with this difference in electronegativity of hydrogen and fluorine, there is a much greater difference. And why is it so? Because fluorine is very highly electronegative, and the hydrogen, you can say, it is very least electronegative. Similarly, if you compare this carbon and oxygen electronegativity difference is not that much high. So due to this reason, it is not that much polar. So you can consider it as a non-polar. And I would make a statement also that almost all of the organic molecules are non-polar. And you know that non-polar dissolves in non-polar. So what are the non-polar solvent that can be available? So benzene is a non-polar solvent, ether. So ether is also methanol, chloroform. Okay. Or you can also term them as organic solvent. Okay. You can also term them as organic solvent or polar solvent. Now talking about the this is scent, or you can say aroma of this aldehyde. So this aldehyde have a very sharp, pungent smell. Pungent, you can think at irritating smell. Okay, so that would hit your mind also, or you can say it would hit your senses. So if you just take a little vapor of those aldehyde and ketone, that would hit your senses and make you say uncomfortable for some minute seconds. Okay, now as the size of the molecule increases, the odor become less pungent and more fragrant. Now this should be noticed, that as we increase the size of the molecule, the odor become less pungent and more fragrant. In fact, many naturally occurring aldehyde and ketone are used in the blending of perfumes and flavoring reagents. So you can be framed a question in this way, that say a flavoring molecule has been taken, or you can say a molecule having a compound having good fragrance has been taken, and you may be asked the question further that it has been reduced to something else, and in that way you can be asked to identify that compound. So in that case, you will be missing the first sentence only, or you will be missing the first information only, that it can be an aldehyde and ketone. So you must be aware about these things, that it is having a fragrant, okay, and it is used in also blending of perfumes and flavoring reagent. Clear? So if I talk about this whole of this slide, then I would say that as we increase the size of the molecule, in case of aldehyde and ketone, their solubility decreases due to decrease in the polarity of the bond of CO. And also the molecule which are having lower molecular mass have a pungent smell, but as we move to the higher one, this their scent becomes more fragrant, and they're also used in the blending of perfumes and flavoring reagents. Now I would do an exercise in which I would try to compare some of the organic molecules and their boiling point with respect to their boiling points. So this is our exercise. So we have an aldehyde here. So this is the aldehyde. We have a alcohol here. Then this is the ether and a normal alkane. Now how you would see all of these? So first of all, let us start with alcohol. So I put up a picture of alcohol which is doing hydrogen bonding. So there is both phenol and alcohol. You can focus on this thing. You can see that there is a hydrogen bonding between each molecule of the alcohol, and as I have told you that this hydrogen bonding has a greater extent, or you can say greater extent of interaction. Therefore it would result in a greater bonding between the molecules of the compound, and hence a higher boiling point. One more thing, if you just calculate each of this having the molecular mass. So if you calculate the molecular mass of each of these, you will see that their molecular mass is also comparable. Okay, so this is clear. So due to this reason, this would have the highest boiling point. So it is placed as the first position. Next, let us compare the dipole-dipole interaction. So two kinds of dipole-dipole interaction can be seen. First is between aldehyde molecules and second is between ketone molecule. Now which one would have a greater dipole-dipole interaction? The one which has a greater dipole moment, because dipole-dipole interaction means the attraction between the negative part of one molecule with the positive part of the other molecule, and the charge will be dependent clearly upon the dipole moment. Now let us compare. So for that I have put up a picture of this three types of carbonyl compound. Okay, three types of carbonyl compound. The first one is your aldehyde, of course, it is formaldehyde. then it is your again your aldehyde, and then your ketone. Now what is the difference in dipole moment? So you can see that as we are introducing R and removing H, we can see an increase in dipole moment, 2.29, 2.5, 2.9. And why is it so? So because the reason is very clear. So as we are introducing this groups, that is R here in place of H, they are giving electrons through inductive effect, that is decreasing the positive charge on carbon and hence decreasing the dipole moment and polarity of this bond. And as we decrease the polarity of this bond, the dipole-dipole interaction will decrease and hence it will have a lower boiling point. Therefore, we have aldehyde first. And if it would be a ketone, we will place it here. So I have just put this thing because it is important, because in case you are asked to say compare between aldehyde and ketone, then it can be used. Coming to ethers, let us compare the polarity of ether with a aldehyde or ketone. Say we are comparing it with a ketone. Now you can see that this both have a dipole moment, no problem with it, but the dipole moment of this ether is smaller as compared to dipole moment of your carbonyl compound, that is aldehyde or ketone. Now what is this? What is the reason behind it? So if you see both of this dipole direction between OR, this bond and this OR bond, you can see that if we resolve it, so we have resolved it in two vectors. So this is in y-axis and this is in x-axis. Similarly, this one has been resolved in y-axis and this is in x-axis. Now one of the component is opposite in direction of each of this. So this two component is cancelled and the left component, they add up and we see a dipole moment in this direction. But the thing that has to be noticed here, that one of the component is cancelled. There are two bonds that are donating the dipole moment, but they're cancelling each other. One of the component is cancelling each other and we are left with one component only. But if you look at this thing, that is ketone, you can see that both of the bond, so there are two bonds, so the both of the bonds are having a dipole moment, or I would say we can take it as single bond also, then no problem in it. But since this bond is smaller, okay, this bond is smaller, so we and it is a double bond, so we are taking two. Now these both are adding in the same direction and not a unit of it, the whole of both of them are adding in the same direction. In the previous one we were resolving it on two axes, but in this case we are not resolving it. You can think of resolution of vectors as division of vectors in two directions. So dividing something in two directions, but in this case we are not dividing it, we are just adding it. And in this division you can see that one of this factor has been cancelled out and one of the factor has been added. Now I have tried to demonstrate this decreased dipole moment with the help of the length of this arrow. So I have put a smaller length of a small length arrow in case of ether, so it has a less dipole moment as compared to your ketone, which has a greater, or you can say large size of the arrow. So the ether is placed after your aldehyde. At last we have a normal alkane which has no such interaction such as your dipole moment or hydrogen bonding. It is simply having your van der Waals interaction, so it is having the least this boiling point. So if I just place the arrow here, so this would be in this way. I will not considering this thing, we are comparing this alcohol, aldehyde, ketone and ether. So this was the exercise. Now this was all about the physical properties. Now I would move toward the chemical properties. So before starting the chemical properties, let us look at the structure of carbonyl compound, which we have discussed earlier, but it is important to for the discussion of your reactivity, because reactivity is clearly dependent upon the structure, that which atom which will react in the presence of reagent, how any substrate will react in presence of any different reagent. So that is dependent upon the charge distribution of the compound, which is well covered in its structure. So as I have told you earlier, I will not take much time on this. So as I have told you earlier that it is a sp2 hybridized carbon in case of carbonyl. Therefore, one of the p orbital is perpendicular to the sigma bond head on head overlap. Now there are two orbitals, one of oxygen and one of carbon. They both will interact and form a pi bond. So this is the pi bond, and this pi bond has a greater charge density in in the direction of oxygen. This is clearly shown with the help of the electron density being you can say fattened at one side, and this is thin at one side on carbon side. So you can see that due to this the pi bond interaction, or you can say interaction between two p orbitals, that the formation of pi bonds had decreased the electronegativity on carbon. Okay, and electronegativity of carbon, not I would say electron density on carbon, and now it will facilitate the attack of nucleophile. So now let us see how this attack happens. So this is the demonstration how the attacks happen. So we have a sp2 carbon here, which has a delta positive charge, which is clearly due to the greater electronegativity of oxygen, and also you can think of it with the help of your pi bond interaction, which has related in a greater electron density of carbon as compared to oxygen. Now we have this thing. So how this nucleophile will attack? So a nucleophile will attack perpendicular to the plane of sp2. So it is approximately perpendicular. I will not say it is perfectly perpendicular attack. This is approximately perpendicular. It is well mentioned here. This angle is different. It is somewhat 107 degrees Celsius. 107 degree angle. That is called Baldwin angle. We will not get into it, but just for information that it is not close to perpendicular. It is approximately perpendicular attack. Now once this nucleophile is attacked, we can see that the hybridization of this carbon has changed from sp2 to sp3. How you would notice this quickly without going into your electron distribution? Just see the number of bond, or you can say just see the number of atoms it has made bond with. So initially carbon was bonded to 3 atoms. Now it is bonded to 4 atoms. So therefore it will be sp3 hybridized. Further, now after this attack, this pi bond moved to on oxygen and creates a negative charge on oxygen. Now it is taken, it takes this H plus from the solution. So we do it in a solution that is having a protic H plus, or you can say a protic solvent. So this nucleophile attacks on this carbonyl center. We get a negative charge on oxygen, and this oxygen takes the H plus to satisfy its you can say octet. This octet is satisfied to remove the electron density or electronic distribution. Clear? So this was about the mechanism of the nucleophilic addition reaction. Now as we are aware about the mechanistic part of this reaction, now we can move to reactivity. Now I would suggest you one thing, that you should be following all of this, because this is a kind of, you can say, pyramid. So we are building a pyramid like this. So if you are not aware about the foundation thing, then you will not be able to depict the reactivity and hence your nucleophilic attack. Okay, so you should be following each of this thing one by one. Now as we know that, okay, we have an attack of nucleophile on this carbonyl center, and how is it facilitated? It is facilitated by the attack of a negative charge on a carbon which is having a partial positive charge. Now what happens if we are changing this positive charge, partial positive charge, in some way by changing the substituent, that is A and B? So based on that, we can change the reactivity, or we can compare the reactivity of two given molecules, that which one will react fast and which one will react slow. Now let us see this. So as it is usual, aldehydes have a greater reactivity. Reason is obvious. We have mentioned the same reason in case of your dipole-dipole interaction. We have seen that the dipole moment of aldehyde is higher due to plus I effect in case of ketone, which is being given on two sides by R. Okay. Now aldehydes are generally more reactive than ketones in nucleophilic addition due to steric reason and electronic reason. Now one more reason comes here, steric reason. The reason I have told you just now, what electronic reason, that is change in charge, or you can say difference in charge distribution. Now what is the steric reason? So if you compare an aldehyde and ketone, you will see that in case of ketone we have R on both sides, or alkyl chain on both sides. If we compare it to aldehyde, we have R on one side but we have H on another side. Now H is smaller in size as compared to carbon, so it would not say inhibit the attack of your nucleophile that is incoming, and this would facilitate a much more easier reaction as compared to your ketone, which has an alkyl group, and it is prohibiting the attack of nucleophile due to high steric hindrance and also your electronic reason. So the same thing written here, that sterically the presence of two relatively large substituents in ketones hinders the approach of nucleophile to carbon compound. So this large substituent, that is R, is hindering the approach of the nucleophile. Approach means attack of the nucleophile on the carbonyl compound. Where in aldehyde, we have only one such substituent. So if you look at aldehyde here, okay, so its structure looks like this. So we have only one R. Clear? Now electronically, the aldehyde are more reactive than ketone because two alkyl groups are reducing the nucleophilicity of the carbonyl group more effectively than in former. Same inductive effect. Now this is normally about aldehyde and ketone, but as you will see the questions, you will be facing many different carbonyl compound other than this aldehyde and ketone. Say we are removing the H, or you can say R, and we are placing X here, that is chlorine bromine. Then we can put S here, that is sulfur or oxygen or nitrogen or oxygen. Now what will happen in each of these? Let us see one by one. Very important thing to notice. Okay, so you can see that first is the halogen group placed. Why is it so? Say one more thing, I would make sure that you should be well aware that the resonance effect is much more pronounced than the inductive effect. Okay, so this should be kept in your mind. There are some say exceptions, and you will notice one of them right now. So here you can see, I would not say there are exceptions, only we are not well aware about this, how this resonance part works. So if you are well aware about how this resonance part works, then there would be no problem, no such problem. Now if you think about any, say this chlorine or bromine halogen, now this chlorine and bromine, they are having high electronegativity. Now you would say, sir, they have lone pair, they must have donated to this carbon atom, and it would have decreased the dipole moment and hence decrease the reactivity. But why is it so? So listen, students, what is happening in resonance? First of all, in resonance, we are donating electrons, which is present in the highest occupied molecular orbital, to an orbital which is having the lowest energy. So we are donating in this way. But if we compare carbon and your chlorine bromine, they are in different periods. Since they are in different periods, therefore the difference between their orbital energy is very high. So as this energy is high, the facilitation, or you can say the ease of say dislocating of electrons becomes difficult, because they have to cover a high energy, or you can say they have to profane, or you can say pass a higher energy barrier. At the same time, this chlorine and bromine are also very highly electronegative as compared to your R, which is carbon in case of ketone. Okay, clear? So therefore, there will be no such donation, or you can say there is no such pronounced donation. There is donation, but that donation of electron is not that much pronounced. But there is a higher electronegativity. So instead of increasing electron density of carbon through resonance, this chlorine and bromine, what do? They decrease, or you can say decrease the charge on the carbon by inductive effect due to higher electronegativity, and hence increase the reactivity of the carbonyl center. Now next we move to your aldehyde ketone. So since I have told that they have a smaller electronegativity as compared to chlorine and bromine, they would not be able to remove the charge, or they would not be able to create a higher positive charge on carbon, and instead this carbon would donate electron. This R dash carbon, alkyl group carbon, will donate electron on the carbon that is to be attacked. Further, we have sulfur. So sulfur is not that much electronegative, and instead of that, it is being able to donate it electron. Now you would say that, okay, you were saying that the difference in your atomic orbital energy would change the resonance effect. But see, students, although the difference is high, but there is no electron removal from the carbonyl center. In this case, we have electron removal, but in this case, we do not have any electron removal. Okay, so therefore, it's say this. And nucleophilic attack tendency has decreased due to decrease in dipole moment. because it is donating electron to some extent, and since sulfur is less electronegative, it is not attracting much of them. Then comes your ester. This is very important to notice that ester is having the lowest one because carbon and oxygen falls in the same period, and they are very good in donating electrons in this way. So if you think of the resonance hybrid would look like this. This is called ester. So it will donate electrons, and clearly it will change this bond length, also the bond character and electron distribution. All of this will be disturbed by the ester. Next comes our amide, which is nitrogen. So we have amide. So since nitrogen is less electronegative as compared to oxygen, it will have a less, say, inductive effect, or you can say electron pull, as compared to oxygen. So they are donating, okay, so they're donating well good, but they're not say taking electrons from the carbonyl center as compared to oxygen, which is highly electronegative in comparison to nitrogen. Next, we have the carboxylate ion. So this one has the least because there is only oxygen, and that is having a negative charge. And you know that as we are well versed that if we have a neutral species, then that would be more stable. So if it is a charged one, so it would just try to delocalize or stabilize their charge in by delocalization. So this will delocalize its charge. In this fashion, this will move here and here. Again, this will revert back. So there is a very high resonance factor in this case, carboxylate ion. Clear? So this was about the reactivity towards nucleophilic attack. Now we are aware about the nucleophilic attack. We are aware about the reactivity of the carbonyl center. Now let us see some examples. So these examples are very important for you to discuss because questions are often asked from here. They are not directly asked. They are being asked in the middle of the reaction. They put some reagents and then they ask you, okay, let's proceed the reaction with the help of 3 reagents. Now suppose one of these reagent is just Cn minus, then you will get confused how you will have to proceed. Now let us move to the reaction. First of all, we have a HCN. So HCN will break into your Cn minus and H2O. Okay. This OH minus is pachylated by water because we have H plus and OH minus from water. So we have Cn minus. Now this Cn minus will attack this nucleophilic center of carbon, and this pi bond will move up to oxygen and create a negative charge on oxygen and Cn. Further, we protonate it with the help of H plus to get our cyanohydride. Now let me make one statement here that this intermediate is not very much stable. It is kind of just shown, but if we put a further reagent, like if you hydrolyze it, so this will quickly form carboxylate ion. So that is a different thing. But for now, just take it for my word that this intermediate is not very stable. That quickly reverts back to your carbonyl compound, which is very much stable. Or this thing also is not that much stable because carbon double bond oxygen is very strong and is a well-versed thermodynamic product. So it quickly reverts into your carbonyl compound. Now I will make a statement that if we use AgCN in place of this, then this would have resulted in isocyanate, by which I mean that in place of Cn we would see NC if we use AgCN. Now that is clearly due to the covalent character between Ag and cyanide, that is silver and cyanide. So this was about addition of hydrogen cyanide. Next we have sodium hydrogen, that is NaHCO3. So if you use NaHCO3, then first of all HCO3 will attack with the help of oxygen atom on this center, and this will create a negative charge on oxygen due to delocalization of pi bond from this between carbon and oxygen to oxygen only, which will be neutralized by the sodium atom. Further, we know that this proton transfer will take place. This is very important to notice that the final product is this and not this. Okay, so this is very important. So this is clearly due to the higher electron, you can say acidity of this bond. This is OH bond. So if we form an OH here, okay, if we form an OH here and O negative on this thing, that is OSO2, so it will look like this. Okay, it will look like this. But what is the difficulty here? Why is it not taking H plus? Because this is stable as compared to O minus, because it can resonate in this fashion. Therefore, this product is majorly favored because this charge on oxygen is stabilized by resonance, whereas there is no such charge stabilization by this oxygen. Okay, clear? Next, we have addition of alcohol. Now you should remember these names also. This is called cyanohydrine. This is called bisulfite addition compound. Next one is hemiacetal and acetal. What is hemiacetal and acetal? So we treat our aldehyde with ROH. Therefore, we got a hemiacetal. Again, we treat it with another molecule of R-OH. Now both of the OH has been removed. We got an acetal. So the one with one OR is called acetal, okay, hemiacetal, and the one with two ORs are called acetal. Clear? Next we have a addition of ammonia and its derivative, and I have named this all derivative in the previous class, so I will not show all of them now. I will just tell that okay, we have ammonia and one of the hydrogen of nitrogen is being replaced with the help of alkyl or aryl OH, NH2, C6H5, NH, NHCl, NH2. So there are 1, 2, 3, 4, 5, 6 kind of derivatives of this ammonia. Now what we will do, we will attack this thing. A nitrogen has lone pair, it will attack here, and the pi bond will move out to oxygen and make this kind of intermediate. Further, this intermediate is decomposed to imine. This is called imine. Okay, and the Z group will be as always on the right side here. Clear? Plus H2O. Now these are all the derivative of this imine. So I would now tell you one more thing. This H2O is quickly removed from the solution as this imine is formed. As I have told you earlier that imine is very pro-reactive to this water. So they quickly breaks into back into your carbonyl compound. So this H2O has been removed to favor the equilibrium in forward direction. So this was these were some examples of your nucleophilic addition. Next we will move to oxidation. This is oxidation. So this two oxidation is very important, that is Tolvin's test and Filling's test. Both of these tests are used to test the presence of your aldehyde group. So if there is an aldehyde group and we are treating it with a Tolvin's reagent, which is basically a complex of silver. Okay, this is a complex of silver. So if we treat it in the basic medium, then this will be oxidized. This aldehyde will be oxidized to your this carboxylate ion. Sorry, it will be oxidized to your carboxylate ion plus silver, H2O and NH3. Okay, silver, H2O and NH3. So carboxylate ion is an oxidized form of this aldehyde. And how do we detect that this aldehyde is present? So as this reaction will proceed, we will form silver. Now what is the advantage of silver? You can see a silvery color, that is whitish color in the reaction mixture. Mirror formation is, it is called as mirror formation. You can see a mirror type thing that is being formed in the solution. Now I would suggest you to balance this reaction and remember this. So you must be remembering the balanced reaction. That would be more appropriate rather than just remembering the reaction that okay, it gives just carboxylate ion and silver and all. You should be well aware about the coefficients, and also it is done in basic medium. Next it is Filling's test. Similarly it is also for aldehyde, but Filling test, how it is prepared, we take filling solution A, that is aqueous copper sulfate, that is CuSO4, plus filling solution B, that is alkaline sodium potassium tartrate. So there are two CO minus in this, and one is satisfied by Na plus, one is satisfied by K plus. This is called as Rochelle salt. So as we treat this filling solution with your RCHO, this will also oxidize your aldehyde to your carboxylate ion. But in this case, the reaction indicator is this formation of red brown TPT. But in this case, we have silver color. Okay. So both of these tests are done to know the presence of an aldehyde group in the given compound. Next is your haloform test. So this reaction is very important. This reaction is very important for you. So why it is done, for what identification? So it is basically done to identify CH3CO group. CH3CO group. So if anything has a CH3CO group, then it will give you this haloform test, and haloform test is mainly done with the help of iodine. Okay, so chlorine and bromine are also used. They will also give the reaction, but you will not see a physical indication in case of chlorine and bromine. Whereas in case of iodine, you will see a haloform yellow color precipitate formation. So how it is done? You treat your CH3CO group containing compound with NaOH, that is sodium hypotite. Okay, and you will get this thing. Now, what are the condition? As I have told, that it should at least contain one methyl group that is attached to your carbonyl center. Next, the iodoform is formed, iodoform reaction with sodium hypotite. What is iodoform? This is called iodoform if we place CHI3 with sodium hypophyte. Okay, sodium hypophyte is NO2P2O3. So if you treat both of them, you will get NaOX, which will react with this thing to give your carboxylate ion. Now it is also an oxidation reaction. You can see that this has been oxidized to this because we have added one oxygen. Now if we use this iodine, that is called iodoform, which is CHI3, you will get pale yellow precipitate. Next, reaction is not feasible with fluorine. This should be noticed, that if we use fluorine in place of X, you will not see the reaction. Now one more thing I should tell you of the previous Tolvin's or filling test, that Tolvin's test or filling test, I would say Tolvin's test is done in the presence of a base. Now what is the effect of this? You have written that 3 moles of base should be used. The effect of this is that if you use such kind of substrate which has only 2 carbon attached to it, and it is an alcohol, sorry, should be an alcohol. So if it is alcohol, then it will give your reaction filling solvent test, because we have a OH minus and it should be secondary. Okay, it should be secondary. So it will take OH, this OH minus will take H from here and will remove this H also, because this system is heated, and it will result, this is not a common reaction I would say, but since it is a O negative charge present in case of secondary alcohol, that can also go to your carbonyl group. Therefore the secondary alcohol can also give Tolvin's test, and you will see this when you will see your biomolecule chapter. Okay, so you will see there that some of the biomolecules, instead they are aldehyde and they are not aldehyde, they are giving your Tolvin's test. Okay, clear? So this was about the haloform reaction. Next we have reduction. We will talk about the reduction mechanism tomorrow, but I will just giving you an overview in today's class, that if we have a ketone group, okay, or an aldehyde group, so if you treat it with zinc amalgam, then it gives your reduced group, that is the carbonyl group has been removed. Otherwise, if you treat your carbonyl compound with hydrazine, then still we get this thing which is being converted further into CH2 on hydrolysis. As I have told you that it is very prone to hydrolysis, and it quickly get converted into your carbonyl compound. But here it is not hydrolyzed. We have used KOH, basic condition, in ethylene glycol, and we have heated it. Okay, plus N2 gas. So this is Clemenson, this is Wolff-Kishner. We will talk about its mechanism tomorrow. So this was for today's lecture. Thank you.